Bonjour, welcome. My name is Brian Goetz, and I'm going to be talking today about our plans for modularizing the Java platform in Java 9 and beyond. So the next big version of Java, major version of course, is Java 9. And Java 9 has a lot of interesting features, but it sort of has one big feature, and that is a module system that goes under the name of Jigsaw. You may have seen details about Project Jigsaw in the press or on OpenJDK. And we plan to apply this module system to modularize the Java SE platform itself, as well as the JDK, which is the reference implementation of Java SE. We make a distinction between Java SE and the JDK. The rest of the world doesn't, but you'll bear with me on that. And in the future, we expect to see it adopted by Java EE, as well as by Java application developers and library developers. So most of this talk is about motivations and why we're doing this and what problems we think it's going to solve. So for the next probably 10 minutes, I'm going to talk about a series of what might seem like unrelated problems, but they may be problems that are familiar to you. And these include things like footprint, startup performance, security, predictability. And even though these seem unrelated, you'll see exactly why it is that I'm talking about them. So Java started out as a small platform. Java 1.0 had maybe 200 classes or so. And there's a little story about the cooked frog that I want to tell. Now, bear in mind, this is a story from the perspective of the frog, not the person who wants to eat the frog. So if you take a frog and you drop him in a pot of boiling water, he's going to jump out. He's going to sense that his environment has turned hostile, and he's going to try to get away. But if you take a frog and you drop him in a pot of cool water, and you set the pot on the stove, and you turn the heat on, the water will warm up slowly, and the frog will splash around in the water until eventually he loses consciousness, and then you get to eat him. So all biological species are trained by evolution to notice rapid changes in our environment, but we're not so trained to notice gradual changes in our environment. So Java, same thing. We started out small. We didn't need a module system in the early days. Java was like I said, only a few hundred classes. Over time, Java has grown into a sort of big monolithic mountain, and the JRE download is now over 50 meg. The JDK download is like 150 meg, and this is a good thing. We added a lot of good stuff. We didn't just pour garbage into it. But as it's grown over time, its monolithic organization has become an impediment for some categories of users. So, because even if you only want a little piece of the Java platform, you've got to take it all. So, one category of users for which this is a problem are those that want to run on small devices. So today, even the smallest devices generally have fairly good processors. They're processors capable of running a Java SE VM. But these devices often have very limited memory. And the size of the Java runtime image is an impediment for these users. Now, ironically, the same problem, memory usage, is also a problem for big devices. So, this is a big machine with a terabyte of memory, cost a lot of money. And because it costs a lot of money, people want to get their money's worth out of it. They want to run a lot of applications on it. And that means they want to slice it into fairly small slices so they can run more instances on them. And so if you're running lots of VMs on your big server, or a server at your cloud provider, one of the key drivers of computational cost is memory usage. How much memory is your image using, whether you're actually servicing requests or not? So by reducing the image size, in addition to improving things for small devices, we can improve application density for big devices and bring the cost of computing down. It's pretty rare that the little machines and the big machines are sort of on the same side of the argument, but in this case they are. So a full JRE is about 55 megabytes on 32-bit Linux ARM, which is way bigger than most applications need. So in Java 8, we kind of made a first swing at fixing this problem, where we invented some things called compact profiles. So we invented a concentric set of profiles. The most basic profile has things like the core collections and XML and JDBC in it. And then the profiles get proceedingly larger and bring in more functionality. And so the Compact 1 profile is about 11 megabytes, Compact 2 is about 17, Compact 3 is 30. And this was an okay start on the problem. It gave a little bit of relief to some classes of embedded users, but it's not very flexible. So if you just need one class from Compact 3, you need all of Compact 3. So application footprint is a pain point for some users. Let's look at another pain point. Startup performance. So Java's peak performance is great. In a lot of cases, Java is even faster than C in measures of peak performance. But one area where Java has historically lagged behind is startup performance. And this makes a certain amount of sense if you think about it. The things that make Java fast for peak performance all tend to slow down program startup, because all sorts of work has to be done when you load your application. Not only do you have to load the class files in off disk, and then they get interpreted for a while, and they have to be compiled from bytecode into native code. And the reason we do all that compilation at runtime is not because we're too lazy to save the compilation state on disk. The reason we do that at runtime is you get better performance when you compile dynamically, because you can compile with information about how that code has been used in this run, as opposed to how it might be used across all runs. So, this is a natural engineering trade-off, but peak performance and startup performance are sometimes at odds with each other, and we've historically erred on the side of better peak performance, and that's generally good, but a lot of users now do have a startup performance problem, and we want to address that. And some of this is also accidental. The jar file format was kind of an arbitrary choice we made in 1995. It's basically, zip file painted a pretty color. But zip files were never meant for loading code out at runtime. And, if you can imagine, you have more than one jar on your class path. When you go to load a class, now you have to open not just one zip file to find that class, but you potentially have to open all of them and search them all in order to find the class you're looking for. And so that was, again, wasn't such a big deal, in Java 1 days when you had, 1, 2, 3 elements on your class path. But, we regularly see customers with 1,000 jars on their class path, and it doesn't scale very well. So this has been a persistent pain point for a certain category of users that we want to address. Okay, more pain points. We got a long list. Security. Some of you may have read in the news some articles about Java security in the last few years. We've done an awful lot of catch-up work and bug fixing work to address a lot of the security vulnerabilities that accumulated over the years. But there are some fundamental ways in which the Java security model is just error-prone, and we would like to not be playing catch-up forever. We would rather have a less brittle approach where we can get ahead of the problem. Essentially, most security vulnerabilities stem from being able to fool the security manager into giving it access to a class it's not supposed to have access to. Generally, these are internal JDK classes. And the security manager makes an attempt to get in the way and prevent this from happening, but hackers are clever, and they find clever ways to bypass that. And so we think the answer is to bake better access control into the VM. So right now, the VM has a mechanism where you can say this class is public, this class is private, but we don't necessarily have finer-grained control in the VM over which code bases can access which classes. That's something that this security manager tries to re-inject after the fact. So to give you an example, here's a list of all the packages in Compact 1 profile. You'll notice that more than half of them either start with sun dot or they have the word internal in their name. Only about 25% of them are actually packages that are intended for applications developers to use, Java Lang, Java IO, Java.net, etc. And so in order to try to make these classes inaccessible when you're running the security manager, by the way, who here runs with a security manager in place? Yeah, I'll pretend it's dark and I can't see any hands, but I know there's not very many hands being raised. The security manager tries to detect access to these packages and make it inaccessible. There's a call that you have to make in various places in the JDK to say, is my caller allowed to see this class? And we have to do this in several hundred places, and if you miss one, hackers will drive a truck through that hole. So this is obviously a brittle mechanism, and you can think of this as a weakness in the initial platform design because there wasn't a sufficient ability to encapsulate the internals in a context broader than a single package. So if you're running in any environment that might load untrusted code, like loading applets in the browser, you're supposed to run the security manager and it's supposed to do this job, but it doesn't do as good a job as we like, and a lot of people don't want to pay the performance overhead of it anyway. So rather than relying on every bit of the platform code to get this right, we want to handle this at a lower level. A somewhat related problem, and this is one that is more of a stability issue in addition to a security issue, is application code using internal packages. So all of these sun.dot packages and internal packages, they're not supposed to be accessible, but of course people use them because you've got a problem to solve, so you go to Stack Overflow and you say, oh, look, there's the answer, and you cut and paste it into your code, and the fact that it uses implementation details, well, that's tomorrow's problem, right? So why should you care about whether or not people use these internal APIs, right? Why is this a problem for you? Why do we think it's a big deal? Well, the reality is when users get hooked on using internal APIs, it means that we have a very hard time evolving them and changing them. And that slows down the rate at which we can evolve the platform. So even if it doesn't sound like, well, what's the big deal of using these APIs? The big deal is the cost of people being able to use these APIs means the platform evolves more slowly, and that's not a good thing. Okay, now here's one that I think everybody has some sympathy with. How many people have felt like they have spent some amount of time in jar hell? Right, that's a lot more hands than the security manager, isn't it? So this is another victim of the story about the cooked frog. When you have just 2 or 3 entries on your class path, everything's easy. But if you have 1,000 jars on the class path, how do you know that you got the order right? Well, you don't. You just kind of have to trust that, or you have to build tools to build your class path for you. And even ignoring the performance issue of doing a linear scan over 1,000 jar files, which is terrible, we've all been in the situation where we've had 2 versions of the same jar on the class path, and we think we're running one version, but there's a different version running, or maybe maybe you had a class path that was slightly different in your build environment versus your deployment environment. That never happens, right? Has that ever happened to anybody? Yeah. So that's not so good. And like a lot of applications, and libraries use the class path for various purposes, like log4j will look for a config file on your class path. It'll call get resource, for log4j.xml. What happens if some jar happens to have a log4j.xml in it? Well, you may be running with the wrong configuration. So these are all different aspects of what we call jar hell, and it's really unpleasant, and it all comes from the fact that our mechanism for selecting what classes to use at runtime is brittle and kind of out of date. So, we would like to say goodbye to the class path and replace it with a mechanism that is more reliable, doesn't require tools to build your deployment image, with the right jar files, etc. So I just complained a lot. Some of that complaining you were sympathetic with. Some of that complaining you thought, well, I'm glad that's his problem and not my problem. But the reality is the problems that I just talked about affect all of us in some way or another. And we believe the root cause of this is that Java is this indivisible monolith. That and it grew by accretion over millions of years, just like this mountain here, and we're not able to pick and choose the parts we want. We're not able to tailor it the way we want. And instead of a monolith, what we would really rather have is a box of Lego pieces, where you can take them and put them together in all kinds of ways and build whatever it is that you want to build. So it would have been great if we had done this 20 years ago. At 20 years ago, we didn't realize we had the problem. Maybe 10 years ago, we started to realize we had a problem, but ignored it for some number of years. But it's not a problem that we can ignore forever. So our solution for this is to add a module system to Java. I guess that wasn't a very big surprise at this point in in the discussion. And it's something we've been working on for a while. We've been working on the Jigsaw project for about 5 years now. And to be quite honest, nobody is banging on our door saying, we must have a module system. Well, all right, some people are. But for the most part, most Java developers don't wake up in the morning and say, boy, it really stinks that Java doesn't have a module system. But Java developers, are concerned with the size of their deployments. They're concerned with startup performance. They're concerned with security. They're concerned with the pace at which we're able to evolve the Java platform. And certainly they're concerned with jar hell. And our belief is that the best way to address all of these problems is at the base, and that is to rebuild the Java platform to be modular. Okay, so what's a module? So a module is a unit of distribution. A module has class files. Maybe it has native code. Maybe it has some resources in it. Maybe it exports some services. And it has a set of packages that it exports. And one key aspect of a module system is that if you have a package in a module and you don't export it, it's not visible from outside the module. Right? So this is a strong encapsulation boundary that says code that's internal to a module is really internal to the module. And it's done so in the VM in the same way that private classes are private, that even if you can get access to the class and try to do reflective stuff on it, it's going to tell you, no, you're not allowed to access that. That violates the access control rules. So the first step in this is modularizing the JDK itself. And we've broken the JDK up into about 50 or so modules. And then we built a bunch of tooling on top of that for managing and building and consuming modules. So Project Jigsaw, like I said, has been running for quite a while. And it's composed of a number of different pieces. So we have the luxury, or burden, depending on how you want to look at it, of having two different governance models within Java. We have the JCP, which governs the specifications that determine what you have to do in order to be considered a valid Java implementation. And we have OpenJDK, which is how we develop the JDK, which is the reference implementation for Java SE. And so within OpenJDK, projects are called JEPs, Java Enhancement Proposal. And within the JCP, they're called JSRs. So 10 years ago, we only had JSRs. We're migrating to a model where more of the design work is done in OpenJDK, and the work of the standards group is to standardize rather than to invent the solution. We think that's going to result in a better outcome. So there were 3 JEPs that have already been completed as part of Jigsaw, and 1 JSR that is currently ongoing. So the ones that have already been completed are breaking the JDK up into modules, so determining what the modules should be, modularizing the JDK source base, which only people who build OpenJDK care about, and modularizing the runtime image of the JDK, which people do care about. And the JSR that's running now is about the specification of the module system itself. How is it that applications are going to declare modules, consume modules, et cetera? All the places where there's language changes and library changes, that all has to go on in the JCP process. So let's go through these one by one and see what we've done already and what we're doing next. So the first part of Jigsaw, and this is one that took many years of painstaking work, was to tease apart the dependencies between different pieces of the JDK and break them up into a reasonable set of modules. And so here is a picture of the module graph how we think the module graph will look in Java SE9. And this is one of those things that's like often obvious in hindsight, right? If I show you what the answer is, you're going to say, oh yeah, well that makes sense. What was the big deal? Why did that take you 5 years? Right? But the hard part was identifying where are all the dependencies. And of these dependencies, which of them are fundamental and which of them are accidents of implementation? And can we group them into logical units that make sense to the developers without there being so many interdependencies that you end up having to pull it all in anyway? So this graph actually doesn't depict the module graph. It depicts the transitive reduction of the module graph, which is a process for removing redundant edges from a graph, because if I showed you all the edges, you wouldn't be able to read it. It would just be like a big bowl of spaghetti. But the cool thing is the data for this graph was actually generated by our build. This wasn't something an artist went and whipped up with PowerPoint. This is actually this image actually comes from our build. So let me break it down. We have two colors of modules. We have orange and blue. The orange modules are those that are anticipated to be part of Java SE9, which is to say the Java specification. So going forward, part of the definition for a new version of the Java platform will include a module graph. The blue modules are parts of the JDK, which is to say they're part of what we deliver in our implementation of Java, but they're not necessarily standardized by the JCP. Sort of going through the picture, at the bottom we have one module called base. This is where java.lang and java util are. Everything depends on base. Because you need Java lang object to load a class, and Java lang object lives in base. So everything depends on base. The shaded areas illustrate the compact profiles that we added in Java 8. So the next ring, the darkest gray, includes base and also includes a few small pieces, the logging API and the scripting API. No actual scripting implementations, just the APIs. The next ring is Compact 2, and that adds in XML and JDBC and RMI. Compact 3 adds in, a number of APIs that are interesting to Java EE developers, things like, naming and, security support. And then you can't quite see it, but there's a sort of oval, very, very light gray arc that covers all of the Java SE components. And those are the ones that are in orange. And then, like I said, there are a bunch of other pieces that are part of the JDK but are not part of Java SE. So things like serviceability tools like JConsole, some of the crypto packages, some of the samples like the hprof profiling agent, which was intended as a sample, but a lot of people actually run with it. And you see up in the corner here, you see some modules for compiler and JavaDoc. These are tools that are part of the JDK. So historically, there's been this distinction of you have JRE and JDK. And this is just a packaging distinction. The JDK just includes more stuff than the JRE does. So rather than perpetuate these labels, which were artifacts of how Java was packaged, historically, if you depend on tools like the compiler, you express a dependency on the Java compiler module, and that depends on a number of other modules that were in what used to be called the JRE. And all of the pieces, all the tools in the JDK have been modularized. So if you need JavaDoc, you can just say, I depend on JavaDoc, and it'll pull in the modules you need. So modules form an acyclic graph. The only module that depends on nothing else is java.base, because everything else does depend either implicitly or explicitly on java.base. So, the game here is pretty simple. To compute the modules you need, you start with your direct dependencies, and you compute the transitive closure of those direct dependencies, according to this graph. So if you need, if your application depends on RMI, you'll also have a dependency on logging, but you don't have to explicitly say, I depend on logging, because we know, well, you depend on RMI, and RMI depends on logging, so at runtime, it will make sure, logging is there. So the first project, JEP 200, which was modularize the JDK, was simply tease this big monolithic bag of JDK classes into a reasonable set of modules, give them names, identify their dependencies, and hope that the granularity of the resulting modules is something that makes sense to developers. And like I said, in hindsight, it looks pretty easy. It wasn't easy. We had a bunch of people working on it for a long time. There's also two colors of arrows on this graph. There's blue arrows and gray arrows. And what that means is the gray arrows are implementation dependencies. The current implementation of this module needs access to this other module. But that's something that could change over time. You evolve the module, maybe it has different dependencies. That doesn't affect your clients. The blue modules are, you could think of them as compile time dependencies or API dependencies, where the SQL API requires the XML API because you're going to see types from the XML packages showing up in the SQL APIs. So you couldn't even compile something that depends on SQL without having the XML packages, because you wouldn't be able to parse the signatures of the methods in the SQL package without it. So we have 2 colors of modules, 2 colors of dependencies here. And just as a quick example here, let me just pop out to a shell, and I will show you a couple things about how this is integrated into the JDK. So no, I'm not. Apparently, I'm not able to do that. Let's see. Oh crap! I had not. Oh wait, there it is. There it is. Okay. Can we see that over there? Okay, perfect. So now I'm going to type without being able to see what I'm typing. So if I say, can anybody read this? So if I ask the JDK, show me what modules you've got loaded, you get a list. Right, so here are all the modules that are part of the JDK build that I happen to be working with right now. So I'm able to build a smaller JRE image, which I'll show you, in a few minutes. But the modularity is built into the JVM. It knows about modules, and in fact, if I pop open the shell, you don't know about this tool yet. So one of my favorite features from JDK 9 is Java is finally getting a REPL. Yay! How many years did that take? So I'm just going to show you an example of how this is integrated into the reflection as well. So if I say evaluate the empty string, it says okay, yes, that's of type string. So if I say what's your class, right, it's going to say that empty string has class Java-lang string, no big surprise. And if I ask it what module you're from, it's going to say this class is part of Java.base, right? So again, not terribly surprising, but this is something that is built built into the VM in a very deep way. We're able to switch back. Excellent. Okay. So moving on. So that was JEP 200, which, like I said, was a lot of work in the background, and then when you see it, you say, what's the big deal? Okay. So the next one is also not very interesting to most people if you don't actually work on the JDK itself. But this was merged into OpenJDK about 8 months ago, which is modularize the source code for the JDK itself. Right, so the way source code was laid out is we had a big source tree, and then below that you have either portable source or OS specific source, and then below that you had either Java source or C source, and then it was organized below that by packages. And so we had to transform the organization to put modules at the top, so that each module had all its own classes, all its own native code, and some modules also had configuration data like time zone files and things like that. And so we had to reorganize the source code. Not really a very big deal, but something that we had to do in order to get there. So one of the things that though that this organization tells you that is interesting is that modules don't just contain packages, but they form a partition of the packages. If java.util is in the base module, it can't be in any other module. Okay, and that has a nice consequence for speeding up class loading, because once you find which module contains a given package, someone goes to load a class from that package, you only have to look in that one module. You don't have to do a linear scan of your 1,000 jar files. So that's that helps us to organize code in a way that's friendly to the VM and improves performance. Okay, so the next one is of much broader interest, which is changing the format of the JRE and JDK that we deliver. This has also been implemented, so if you download the latest JDK 9 sources and build it, you'll get a modular JRE. So it used to be the layout of the JRE was you had a bin directory where you had launchers like Java and Java-C, And then a lib directory, which was just a big undifferentiated bag of stuff, including some like editable configuration files, which aren't libraries, and some native libraries, which should not be editable, and a bunch of other stuff, and this big monolithic jar file called rt.jar that had all the classes for the JDK. So we reorganized this so that rather than having one big rt.jar, we have a bunch of modules. I'm not going to tell you what form these modules are in because there's a lot of different options, and we're trying to maintain some flexibility to lay things out on disk in a way that's most that we can optimize at runtime. But we've also separated out things like editable configuration files into a const directory, which is a sensible thing that I don't know how we managed to not do that 20 years ago, but we finally got around to that. But like I said, the important thing is the organization of the JRE is now modular as well. Okay, and a bunch of things went away. So the endorsed standards mechanism went away, the extension loader went away, rt.jar is going away. Okay, so if you ask the class loader to load a class file as a class, it will give you back a URL. And that URL will leak information about how things are organized on disk. So it'll say, well, this is a jar URL, here's a path to the jar file, and then within the jar file, here's a path to give it. This is kind of messy. How many people here have had to mess with this? It's fiddly and not fun, right? Right, okay. So now it gives you back a URL that starts with JRT, Java Runtime. And what this does is it abstracts the organization of the runtime so that it doesn't matter whether your runtime is stored as jar files or JMod files or exploded files or a JImage file, whatever, you're able to access the Java runtime using this URL. And similarly, there's an NIO file system. If you want to access built-in classes and resources, you can do this with an NIO file system. So we put a layer of abstraction between applications and getting at pieces of the JDK. So you'll see a pattern here, which is rather than letting people make assumptions about the layout of things on disk or about the organization of the JDK, where we're taking things away, we're also sticking APIs in between the application and the JRE so that there becomes a supported way to do what you want to do. So we're not just taking away things, but we're adding better ways to do those same things. There'll be some migration pain, there has to be, but we're trying to keep that to a minimum. Okay, so let me walk through an example. How do modules interact at compile time? So modules have names, they contain a set of packages, they have a set of dependencies, which are other modules, and a set of exported packages. We've got our java.base module, and it has some packages in it, including, say, java.lang. Now the packages that are exported are visible outside the module. The packages that are not exported are encapsulated within the module, even to reflection. So let's say we've got another module over here, java.sql, and it has the java.sql and javax.sql packages in it, and it has a dependency on java.base because everything has a dependency on java.base. And it's going to, it's going to use some types from java.base like string in its API. Straightforward so far, right? So in this model so far, we haven't exported java.lang. So if we tried to compile java.sql, we'd get an error saying java.lang is not exported by java.base because non-exported packages are encapsulated. Now, obviously, that's not how we want it to work, right? You're supposed to be able to see classes like string. So there's a list of exports associated with each package, and we're going to say export java.lang to everybody. And then this problem goes away. What we see now is the types in java.lang flow into java.sql. So the blue arrows mean visibility of types. The gray arrows are dependencies between modules. Okay, so obviously we want to add an export to these JavaSQL and JavaX SQL packages because we want clients of JavaSQL to see them. So, all right, let's keep going. Now we've got some implementation code in java.sql that's using a service of the JDK, which is a caller-sensitive reflection, to say, is my caller allowed to see this class? Because it has to know whether you have access to the driver class. And Well, if we do the obvious thing here, we're going to get the same compilation error. Sun.reflect is not exported by java.base. We want Java SQL to be able to see sun.reflect, but we don't want the whole world to see sun.reflect, because otherwise we'd have the same problem we have now. So we can make a qualified export, and we can say java.sql becomes visible, sun.reflect becomes visible to java.sql, but not to everyone else. All right, so let's keep going. There's another module, the logging module, and java.sql uses the logging module and in fact has types like logger in its API. So we've got a module, java.logging, it has a package java-util logging, it's exported to everyone, and java.sql has a dependency on that. So, all right, we're good now. So, and of course, since everything depends on java.base, Java logging depends on java.base. And in fact, java.logging also needs access to this reflective stuff, so we've added that to the access control list. And now let's, an application module comes along. So the application module says, I'm com.foo.app. I depend on java.sql, and of course I depend on java.base. And so the types from both the base module and the SQL module are visible to the app. Pretty good so far, right? All right, so now here's a problem. We call the driver manager, we say, get me your logger, and now we want to call the info method on that logger. What package is that info method defined in? Java-util logging. So we need to make sure that the types that are exported by java.logging and that are part of the Java SQL API are visible to applications. And we could have said, okay, you've got to add all these other modules to your dependency, but that seems kind of messy. So instead what we do is we have two kinds of dependencies, as I said earlier. We have implementation dependencies, which is I need this at runtime, and we have API dependencies, which say this module is really part of my API too. And what that means is it's as if those type names are implicitly re-exported by java.sql, so any of its dependencies can see that. So this all sounds very complicated, but it's actually, quite simple, because all the app module had to do was say, I depend on Java SQL. And if Java SQL has its dependencies correct, then you don't have to worry about all of that. You get all the types from Java SQL re-exports all the types from Java logging, and everything's good. And of course, we can have some packages that are not actually exported at all, and those are completely encapsulated. So this may have sounded complicated because I was describing all the mechanics of it, but in terms of what the application has to do, all it has to do is say, I depend on java.sql, and all of that just works. Okay, so what's in a module? Modules have classes and resources. They also have module metadata. Maybe they have native code. And we could have found a way to shovel all this extra metadata into jar files. We could have put it in the manifest or something. But like we said earlier, jar file is kind of a terrible format for runtime use anyway. So we've got a new file format called JMod for encapsulating modules. You can still put modules in jars if you want. There'll be a modular jar format. If you like jar, you can keep using jar. But we're gonna deliver these as JMods because it's faster. So okay, how do you make modules? Well, there's a new tool. It's called, big surprise, JMod. No mystery here. And it's like the jar tool. You can use it to make JMods and view the contents of JMods. There's also another pretty cool tool, which again you might think is 20 years late, which is an optional linker called JLink. So JLink is a build time linker, and it can handle as input formats, class files, jar files, JMod files, and produce lots of different output formats. And the reason this is important comes back to the goal of startup performance. There are a lot of optimizations where it's really too early to make them at compile time because Java is dynamically linked, and we might undermine the semantics of the program if we made them at compile time. So we do them at runtime, but runtime is kind of late to do them, if you really care about startup performance. And so as an optional tool, you can run JLink to do certain optimizations at link time, which is nice, and you can also use it to build a complete modular runtime or a custom JVM image that has just the modules you want. So if your application only depends on java.sql and java.logging, you can package a custom JRE that just has Java SQL and Java logging and its dependents and distribute that. And so that reduces download size and it's reduces image size. So, JLink is sort of the, Swiss Army knife for slicing and dicing different formats of Java distributions. And like I said, can also do a lot of optimizations at link time. All right. So, how does this affect you guys? So there's no gain without pain, right? If you're using these packages, you're going to have to find a way away from them. Now, a lot of these have been internal just for accidental reasons. And they're perfectly safe, they're perfectly reasonable, and for those, we're just making public supported versions of them. So if you've used sun.misc.base64 decoder, there was no reason that had to be in sun.misc. We moved it into the supported Java libraries. If you're using things like sun.misc unsafe, life is going to be a little bit harder for you, and we are, in the process of making safe supported APIs available for most of the things that it does, although it may take some time to get there. Now, we didn't do this randomly. We, did extensive scans of the code that's in Maven Central to determine which internal APIs are being used and by how many different packages, and we used that to prioritize, which APIs that we need to produce supported versions of. Now, if you're wondering, do I use any internal APIs? We have a tool for that. So there's a scanning tool called JDEPS, which is it's actually being shipped with Java 8, so you can run it now against your production code. And it will tell you what internal APIs you might be depending on, either directly or indirectly, because maybe you don't use them, but you use a jar file that uses them. Which is great because now you can, fix your code sooner rather than later and not get surprised when Java 9 comes along. All right, what else has changed? If you depend on the structure of the JRE, like you go looking for rt.jar or tools.jar, you're not going to find it. So those jar files are just going away. They've been replaced by a more flexible way of saying, let me have access to these runtime files that are part of the runtime image, but you're going to have to migrate to those tools. So, these bits are going away. And, various assumptions about what is located where in the JRE, those may also become invalid. So there's a little bit of pain, mostly more for framework developers and tool vendors like, Eclipse or Ant. Which are generally the big offenders of going and using rt.jar and tools.jar directly, but they should know this is coming and they should be able to fix it before it's a problem for anybody. Okay, so last bit of what's left to do. So remember I said Jigsaw had 4 sub-projects, 3 of which were already completed. I showed you those. You said, boy, those are boring. Where's the interesting stuff? Well, the interesting stuff is all in JSR 376, which is the JSR for the Java Platform Module System. So this JSR was convened probably 3-4 months ago at this point, and is in discussions now. And the goal of this is to define the mechanisms by which the module system touches the developer. Now, we already know some of the answers about what modules have, right? Modules have to have names. They have to have dependencies. They have to have packages they contain. What the syntax of the file format that describes the module metadata is being discussed now by the JSR Expert Group. Similarly, I gave you a hint that there was a reflection API where you could call class.getModule. What does that API look like? To be determined. Similarly, what features do we have to add to make life easier for developer tools like IDEs or build tools, like Maven or Gradle, in order to be able to interact with the module system? And similarly, if you've already built a package using Maven. So you have a POM, you've already named your dependencies. We don't want to make you name your dependencies again. Not only is that extra work, but if you do it twice, they may not be consistent with each other. So we definitely want to have a way to extract as much of the metadata as we can. If you have an existing Maven POM, the details of that, need to be worked out. And similarly, if you're running on a system that has a package manager like RPM or Yum or apt-get, it should be easy to take a Java module and turn that into a package whose dependencies, whose Java dependencies turn into RPM dependencies. And the last big area that we're currently working on is what about EE containers that have to be able to load different versions of the same module for different web applications. And there's an API for that where you can dynamically create a new module graph and bind it to a class loader that containers are going to use. So these are the things that are going on right now. There's an OpenJDK project called Project Jigsaw. There's public mailing lists. There's public Jigsaw builds. So if you're interested in getting involved or trying it out, you can download it and play with it. If you want to get involved in the process, you can show up on Jigsaw Dev. So with that, we've got about 5 minutes left, and I'm happy to take some questions. So I can't see anything. So wave your hand furiously if you have a question. Okay, front row over here. Gentleman in the pie shirt. You. Go ahead. Oh, you're waiting for the microphone. I get it now.
Jigsaw is all about modularization, and I was thinking how it relates to OSGI.
Okay, never gotten that question before. Various versions of this question. What is the interoperability story between Jigsaw and OSGI? Why didn't we just take OSGI as our modularization story? So we actually worked at that pretty hard. We spent several years trying to figure out if there is a reconciliation between the modularization needs of the JDK and OSGI. And what we found was that OSGI was a bad fit in the sense that it was both too large and too small at the same time. OSGI necessarily has to live on top of the Java platform. We were not bound by that constraint, and we had certain goals that said, we want to get modular boundary enforcement in the JVM, not added from the outside. The other reason why OSGI was not necessarily as good a fit as you might initially think is it's a lot more than a module system. It has a lifecycle management and services, and you can dynamically, replace jars, on the fly. And there's a lot of complexity that comes with that we didn't feel was needed for people who just want to be able to write reliable Java programs and not have to fiddle getting their class path right. So we spent a significant amount of time trying to figure out if OSGI was part of the solution. And, a lot of people say, oh, those guys at Sun/Oracle, they have to invent everything themselves. We spent a lot of time trying not to invent something before we gave up and invented something. So, but there are folks from the OSGI, whatever the governing body is called, that are on the JSR Expert Group. So we're certainly learning from what OSGI learned. Okay, more questions. I guess we have some folks over here. Pays to sit close to the front of the room.
When speaking about modules, you said that module is defined as a set of classes, resources, and services. What's a service in this case?
So, are you familiar with the service loader mechanism in Java? We have a mechanism called service loader, which is a dynamic lookup mechanism. So you define an interface called, XYZ provider. And then you ask service loader, find me any providers of this XYZ service on the class path. And so it's a way of supporting things like application plugins, where you say, I'm a consumer of this service, and I expect modules that are in my system to be providers of this service, and the module system provides a way to allow consumers of the service to find at runtime who provides the service. And so it's a kind of loose coupling configuration mechanism, so that rather than having to have a config file that says, my plugins are these 19 classes, Individual plugins can say, I'm an XYZ provider in their module manifest, and you can say, I require the services of an XYZ provider, now tell me who they are at runtime. It's a very lightweight, simple mechanism. There's not a fancy service lifecycle management, but it does provide a way to say, I export the service, I consume the service, and have those people meet. So a few more questions. Did I see a hand going up? Yeah, there's a hand back there. And I think this will probably be the last question, so make it a good one. No pressure.
Are there any plans to make the modules downloadable on the fly, or will we have to download the whole package at one time?
So that's an excellent question. I don't know the answer to that question. Obviously, we've thought about that question a lot. We certainly have no plans to run an open Maven Central style repository where people can push modules to our service and have us distribute. That's not something that's in Oracle's DNA, so the lawyers would never let us do that. But there almost certainly will be a way, and we don't know what it is, but there will be a way for you to download the Java SE modules individually, the Java EE modules individually, any modules that Oracle publishes. There will be both a programmatic and a website delivery mechanism for that. For third-party modules, we expect people will continue to use Maven Central. We have no reason to try to compete with Maven Central. That's where people go for code. Great. Put modules in there, we'll find them. So that's the story. I don't know the specifics, but there has to be. We have to have that. We just don't know exactly what it'll look like yet. So, all right. So it's telling me time's up. So thank you very much, everyone.